Hi, how's everybody? This is the lecture for uh, multiple multiple cash flow model, time value of money, right? Actually, multiple cash flow model is um, as opposed to single cash flow model, and it's of course part of the time value of money model. Now, in our last class, we completely um, wrapped up the discussion about the single cash flow model and the possible equations that can or equations and formulas that can arise from the base single cash flow model, which is called compounding. Now, we have moved on to the multiple cash flow model. So basically, what does multiple cash flow model mean? Well, in the single cash flow model, remember that there's only one cash outflow and one at time zero, and one cash inflow at time n, or at time uppercase T. And you understand uppercase T means terminal time. So as an example, you put $10,000 in the bank today, and that's at a cash outflow at time zero, right? And then if the market interest rate is 10%, and 5 years later, and that 5 years is your timeline, so that's the terminal time uppercase T, right? And so 5 years later, what's going to be your future value? And if the future value is some X amount of dollars, it would be, of course, greater than 10,000. If at 10%, if it gets compounded for 5 years, it would definitely be greater than, much greater than $10,000. It would be just, off the top of my head, if it is 10%, it would be more than $16,000 at least. Now, but anyway, that is the future value, and you will withdraw that money from the bank. So that's one cash inflow, right? So that's why it's called the single cash flow model. But then what will be an example of multiple cash flow model? Now, suppose you have decided to go to a graduate school, right? And then the graduate schools cost, of course, a lot of money, right? Of course, it would cost less than 4 years. I mean, if you are going to just a 2-year master's program, let's say MBA program, and the MBA program would cost as much as what an undergrad program would cost per year. So you understand it would be at least about $40,000 to $60,000 a year. Then for over 2 years, it's going to be at least like 100,000, 80,000 to $120,000, depending on how prestigious and respected MBA program you are going to. But let's say that costs too much money, right? And so let's say you settle for CUNY graduate school, right? And CUNY is relatively more affordable than Ivy League schools. So let's say it is about $30,000 a year. But this is master's programs are 2-year programs. Basically, if you finish ideally within 2 years. So you have a target amount here, right? When you go to graduate school, you will need to at least $60,000. But now, how do you raise $60,000? That's the big question, right? Now, there are two ways, roughly, about two to three ways to um amass or accumulate $60,000. But of course, you will need some timeline, right? So suppose you are a freshman right now and you have 4 years to graduate. And then not just 4 years, but most good, decent graduate school MBA programs require some work experience in a large corporate structure. So if you ideally graduate in 4 years, then and if you immediately land a job in a large corporations and work up some work experience, right? Rack up some work experience for about 1 or 2 years. So at least it would take 5 to 6 years before you apply for graduate school and get admitted. But let's say ideally, right? Um, it takes 4 years for you to graduate with bachelor's and land a job immediately and work for 1 year. So let's say your timeline is 5 years, right? So 5 years later, that means 5 years later, you will need to have $60,000 ready, right? But then how do you get to that $60,000? Well, one way you can do that is by putting some principal into the bank, right? Into a bank account. For example, if you have something like a $40,000 today, put it in a bank, and if the interest rate is good, very good, right? In 6 years, it will accumulate, right? It will get compounded and accumulate to accrue to 60, may accrue to 60,000. Well, we don't know that yet, but it all depends on how good the interest rate is. But once again, we know this is not very realistic, right? Because who has $40,000 now? I mean, you're just all about 18, 19, 20, 21, at that age, who has $40,000 under your name? That's not likely, right? So, more realistic and practical option is to save every month, right? So if you let's say you get a part-time job, and from the part-time job, let's say you can save $800 every month, $800. Now, you have to save a regular amount. It shouldn't be, irregular amount, or and you should be making a deposit at a regular interval. And the regular interval in this case would be monthly, right? At the end of every month. So that's more, practical scenario, more realistic, right? And well, the other scenario was, you may make a deposit, but not at regular interval. You may make a deposit once in a while, here and there, right? Sporadically, a deposit of irregular amount. But then that kind of that can be also considered multiple cash flow, but that is not the model we are going to pursue, because there is no predictability, right? There's no predictability in that case, because you don't know when your next deposit will be and how much will be. So we will basically eliminate that case, and we will focus only on the case of regular amount deposited at regular interval. Now, that kind of cash flow is called annuity, right? Now, the term annuity sounds like something annual, but no, it doesn't have to be annual. It can be monthly, it can be weekly, it can be quarterly, it can be daily. The point is, annuity is um, a payment or deposit made at regular interval in the same amount all the time, in constant amount. Okay, so think about it. If you are saving through annuity, right? So in the first month, you make $800 deposit, and this and since your timeline is 5 years, there are 60 months, right? And then you make a deposit at the end of the first month, at the end of every month. So then the first deposit will, until the month 60, right? It will earn interest, monthly interest, right? Compounded 59 times in total. Isn't that right? Because you're making a deposit at the end of the year. Now, the other model is called, oh, this is called, I'm sorry, I forgot to mention the name of this type of deposit. It's called ordinary annuity. Ordinary annuity, because it's called ordinary, right? Making a deposit or payment at the end of each period, right? Now, and this is more likely because you cannot make a deposit at the beginning of the month. Why? Because the money you deposit comes from your paycheck from your part-time job, right? And you get paid at the end of the month, or you get bi-weekly. That means you're getting paid at the end of each 2 weeks. So but you cannot make a deposit before you get paid. I mean, you cannot get paid before you start working, right? So there's no way you can make that deposit at the beginning. Of course, unless you make that deposit uh, out of your own pocket, right, from the money you already had. But let's say you don't have anything, you don't have any money in front in advance. So the money has to come from uh, your paycheck, right? Then this deposit will start from the end of the month. So that's why there will be 59 compoundings of monthly interest rate, right? Think about it. If the interest rate, you're making a monthly deposit, and if the compounding is monthly because you're making monthly deposit, right? Each month, that $800 that you deposited at the end of the first month will earn interest every month until the end of your timeline, which is the end of month 60. But since you started from the end of month 1, there will be 59 compoundings until the maturity, right? Makes sense? Now, the type of, okay, so this, let's just, quickly go over our scenario again. Our scenario is you're making a deposit of $800 for 60 months, and the first deposit will be counted 59 times. That means then second deposit will be compounded 58 times, and so on. Now, just roughly, just let's do a rough, thought experiment. I mean, all these $800 alone, there will be 60 deposits of $800, right? That alone will be what? $48,000, right? 800 times 60, $48,000. That's principal alone, right? But this is not made at time zero. This is not deposited at time zero. It's spread over 60 months, right? So think about it. With $48,000, with good interest rate, it may be able to your uh, future value or the maturity value to 60,000, right? But just to make it more manageable, because 60 months is, it's very uh, tedious. I mean, it's not that long, but it's very tedious to actually to work with. Let me uh, bring it down, scale it down to a smaller example. Now, the first, okay, let's take a look at this slide. The title is FVA. What does that, what do you think it stands for? Stands future value of annuity. Okay, and then I'm going to get to the other one shortly, but first, let's take a look at this scaled down version, right? Scaled down example. In this example depicts an annuity, annual deposit, annual annuity of $1,000 at the end of the year for 5 years, right? Now our question is, what's going to be the total amount or the future value of this annuity at the end of year 5? Now, let's take a look. If the interest rate is 20%, right, the first deposit, 1,000, will earn interest, right, 4 times compounded. So that's 1,000 times 1.2 raised to 4. Because there will be 4 compoundings until the maturity, right? 1, 2, 1, 2, 3, 4, right? Second deposit of 1,000 will earn interest 3 times compounded. Third deposit will earn interest 2 times compounded. Fourth deposit will earn interest once. And the last deposit is only technically called deposit, but if you think about it, you're making that deposit at maturity. So that means, in reality, it's almost like, dipping your tortilla chip into the salsa and just take it out. The minute you, right, the instant you put the money in the bank, you take it out. So there is no time for the interest to accrue on this deposit. Make sense? It's like, dipping the salsa, but take it out so quickly, there's no time for the salsa to, stick to the tortilla chip, right? Just like that. So then think about it. The total amount will be, right? The first $1,000 deposit will earn interest 4 times compounded. It's going to be this. Second one will be this. Third one will be this. Fourth one will be this. And since this one doesn't earn any interest, right? It's just 1,000. And then 5 years later, the total of that will be this. Okay? That's the future value of annuity. Now, this is ordinary annuity because all these deposits are made at the end of the year, right? At the end of each period. Now, let's take a look at another example. And in this other example, also scaled down version, right? This annuity starts from the beginning of year 1, so time 0. So in this example, you're making a $5,000 deposit or payment. I mean, deposit and payment are, it can be called interchangeably because they are eventually the same thing. You just, turn the table around. Deposit is payment. Anyway, um, so first $5,000 deposit earns interest, 10% interest, right? 10% interest, 5 times compounded. If the interest rate is 10%, right? Look, this deposit earns interest once, twice, 3, 4, 5 times, right? And the second deposit earns interest once. A third deposit earns interest twice. Fourth deposit twice. I'm sorry. Third deposit earns interest 3 times. Fourth twice. Even the last deposit earns interest once. Okay. Now, this type of annuity is called annuity due, right? Meaning the deposit or payment is due already at time 0. In other words, it's already due to begin with, right? So, in of course, the future value or the total amount, a calculation of the total amount of future value is simply the same. You find the future values and sum it up, and in this case, it comes to this. Now, so you might wonder, if it was the same scenario, and if this was, not annuity, ordinary annuity, but annuity due, so how much will be the difference in the future value? Now, if you think about it, if we had $1,000 here, if we had, if we started making a deposit at time 0, another 1,000, then you only have one more term, which is, 1,000 times 1.2 raised to 5, right? And then you don't have this because this one will drop out because 5 deposits at the beginning of the year, so this one will drop out. And then if you compare them, right, compare those two scenarios, the only difference between the two is actually one more compounding. Isn't that right? Haven't you found that? Because if this was made at the beginning of, right, if deposit was made at the beginning of the year, that's going to be 1,000 times 1.2 raised to 5. And it goes all the way to this, and just, without this, right? Without just this one, the last deposit. So then think about it, comparing this series of annuities and with the other one, right? With just one more. Think about it. This one has one more compounding. In other words, the first deposit has one more compounding. Second deposit also has one more compounding. Third deposit has one more compounding. Fourth deposit has one more compounding. Last deposit has one more compounding. And just ignore, think about it. The time starts from here. This is time 0, time 1, time 2, time 3, time 4, right? And there will be time 5, but there's no deposit at that point, right? You see that? So the difference between the ordinary annuity and annuity due is one more compounding, right? Now, so then that gives us an idea. How do we calculate, how do we make it easier to calculate the annuity due? Well, we're going to also talk about this later, but that means you can recycle if you have ordinary annuity. If you have solved it as an ordinary annuity, all you need to do is recycle this and give it one more compounding. And you might wonder, oh, why do you have to do that? Can you not just start doing this from the beginning like this? Look, this is a scaled down example. It's really a minimal scale version. Um, think about it. Even our scenario, even our example of graduate school fund, right? How do you raise graduate school fund, right? In that example, you are dealing with not just 5 deposits, but 60 deposits, right? It's 5 years, but not annual deposit, but monthly deposits, 60 monthly deposits, right? So how would you handle 60 monthly deposits this way? There is no, I mean, it's not undoable, right? But it's going to be very tedious if you are going to do it this way, right? This is very elementary way of going about it, right? In other words, um, even a eighth grader, sixth grader can understand this, right? That's how watered down the example is. But anyway, because this is pedagogically easier to uh, convey the idea, right? This example is uh, useful, but in reality, there is hardly a case you can do it like this. So then, how do you actually, do that? So, actually, I already introduced a formula for that. Our next, then the question is, of course, this formula is showing you that, basically telling you, future value of annuity is equal to payment. Payment means deposit, right? They are, I told you, they are the same. Um, if you're at the paying end, that's payment. If you're at the uh, if you're making a deposit, and if you are saving money, right, that's deposit. And if you have borrowed money and paying back, that's payment, right? So it's just the same thing um, from different standpoint. So that's the deposit, and 1 plus R. This R is, of course, the periodic rate, the monthly rate. This N is the total number of compounding, which is 60 in our example, minus 1 over that periodic rate. Okay, we can use this formula to get to our, find our solution. In other words, how much those $800 will um, accrue to, right? We're going to get to that soon. Uh, but let me switch to, I mean, let's start from, let's build that concept from this assumption, right? A very simple diagram. And let me switch that to switch the screen to a whiteboard. So let me stop sharing this screen and switch to whiteboard. All right. So do you guys all see this whiteboard? Okay. If you see, let's start with the. All right. So basically, how do we? Our question is, how did we get to that formula, right? In other words, future value of annuity, right, equals payment times 1 plus r raised to n minus 1 over r, right? And how, right? That's our question, right? So let's think about it. And this will take time. So we may come back later to actually, see how the through, steps of derivation, we can see later how this formula is derived. But ignore this for now, and let's see. So let me erase this. Ignore this for now, and let me start from the very crude concept, right? So future value of annuity is like, well, think about it. First of all, the first deposit, right? Once again, payment is deposit, right? Will earn interest by the time you reach your future, which is, 60 months later. The first deposit, monthly deposit, that's monthly, will earn interest how many times? It will earn interest 59 times in our scenario. Isn't that right? You remember that? 59 times. Why 59 times? Once again, because you're making a deposit at the end of the month. Counting from that point, end of the first month is the beginning of the second month. So counting from that, it will be a 59, not 60. So in here, I'm not going to write it as 59, but write it as t minus 1 raised to t minus 1. So the uppercase T is what? That's the terminal time. So in our example, it will be 60, right? So t minus 1 will be 59. And then the second deposit will earn interest. One plus r, right? Sorry, r here, raised to t minus 2, right? And we know what then the rest of it is, and that's going to be the third deposit will earn interest, t minus 3 times, so ellipsis, and then, so then next one, as we move closer to the end, right, to the terminal time. Now, the third from the last deposit will earn interest 2 times, right? And the second from, I'm sorry, that must be payment, right? That P. And the second from the last will earn interest. It's so difficult to write with, mouse. It will earn interest at least once, right? Plus R. And the last deposit, I told you, last deposit, this is like 1 here, right? We don't have to write 1. The last deposit doesn't earn any interest, right? Because you are making that deposit at the end, and at the end of month 60. And when you make that deposit at the end of month 60, you will just, take it out right away, right? But also mathematically, you can write it as 1 plus r raised to 0, right? You understand what that is? Remember, anything raised to 0 is what? 1, isn't that right? So that means this term, although it is there, eventually it is just 1, isn't that right? That's only 1, right? So if it is 1, anyway, this payment will, this thing will just reduce to just payment, right? You get that? Now, however, this is a very tedious way of writing it because, look, I just used ellipsis. That means I truncated in the middle, right? If I didn't truncate it in the middle, what does that mean? I will have to write it all the way from t minus 1, 60 terms, all the way from here to, all 60 terms. Now, that's called a polynomial mathematically. Polynomial means literally poly, many, right? Nomial means, terms, right? It means, multiple terms, polynomial, right? So that is very tedious to write it this way. So we know better. Is there a better way we can do this? Yes, of course. We use summation sign, right? Summation notation, right? And so we're summing up all payment times 1 plus r raised to n, where n runs from 0 to t minus 1, terminal t minus 1, right? You get the idea then? This is a very nice way of making that long polynomial very compact, right? It's a nice way of expressing in a very long polynomial, repeating, right, recurring terms in a very compact way, right? So think about it. When n is 0, that's this, right? It becomes this. When n is 1, it becomes this, right? Because n runs from 0 to t minus 1, and you are summing them. When n is 2, it becomes this, right? When n is t minus 2, in this case, 60 minus 2, so 58, it becomes this. When n is t minus 1, it becomes this, right? When n is 59. So you're summing up all of them. Now, so that's nice, right? In other words, it's going to be, this is going to be $800, and this interest rate, if the interest rate is, annual rate is 6%, we know what this is going to be. It's going to be 0.5%, right? It's going to be, so then our next question is, oh, that's wonderful. That's nice. We can nicely capture it in a very compact expression. But then, does it really help us actually calculate our future value? That's another question. Why? Because if you actually plug in the number here, right, $800 times 1.05 raised to, 0 raised to 1, when it is 0, it's just $800, right? But that means you need to run this all over again. You have to actually do this all over again. This is, in other words, then what does that mean? Now, this is only a nice way of compressing, right, in a succinct, expressing this in a succinct way. It just doesn't, but it doesn't really help us to calculate it, right? You understand? So then, how do we calculate it? So we have to use the reduced form, which is basically payment times, right, 1 plus r raised to n minus 1, okay, over r, right? Now, that's the formula we need to use. And this is reduced. I mean, this formula doesn't just drop from the sky. It just doesn't pop up from the thin air, right? Uh, there are steps of derivation. This formula is derived basically from this, and there are steps of derivations. Um, I will not show you at this time because it will take a lot of time to. It will take about 10-15 minutes, but uh, we're gonna get to that later. But right now, we want to use this formula to actually solve our graduate school fund question. You understand? Okay. So let me switch to an Excel file. Okay. Uh, okay. So let's see. Okay. Do you see this Excel file? Okay. Now, this is, of course, this is the file we've been working on. Previously, we were on single cash flow model, right? This is the time value of money, right? And previously, we were on single cash flow. Now we are on multiple cash flow. So you need to, you gotta, uh, click on this bottom tab that says multiple cash flow. Now, when you open it, maybe these cells would be already filled in. So I want you to clear out all the highlighted cells when you open it. Right? All right. Now let's think about this. This is exactly our example, our graduate school fund example. You recognize that? You all recognize that? Because this is your monthly payment or deposit, right? And your APR, the prevailing market rate is 6%. Your timeline is 5 years. M is 12, right? M is 12. That's monthly, because it's monthly deposit. Then what do you need to do? We will need to first find the periodic rate, the monthly rate, and how many compoundings actually happen over 5 years, which is something we have done already previously. So it's not difficult. You just divide 6% M, APR by M, gives you 0.5, and 5 years times 5 times 12. Of course, everybody knows this is even a second grader can tell, third grader can tell, right? 60 months, right? 5 years is 60 months. Now, future value of annuity, we know the formula. The formula is there, right? We did that. So all you need to do is payment times or deposit times, open parenthesis, 1 plus R is to n minus 1, close parenthesis, and divided by R. Okay? Hit enter. We got that. And some of you may say, some of you got excited and say, hooray, we got it. No, we got it, but that's not the final answer. Why? What was our question? Our question was, you want to go to graduate school in 5 years, and it will cost $60,000, right, to finance your, to pay for your graduate school for 2 years. So our question was, if you work part-time and save $800 every month, you accumulate enough money at the end of year 5 to pay for your graduate school. So that is that is your final answer. Is that enough? I mean, did you reach the target future value, right? You had your target future value, which is 60,000, right? So arriving at this is only half the answer, right? You shouldn't lose focus. You shouldn't lose the perspective, right? You should. The reason you calculated this is to see whether you can reach the target future value. So you have to answer that. Oh, of course not. This doesn't come to your target future value. In other words, it still undershoots your target future value by about $4,000. Okay, then how do you, to reach that target future value, you have to try out different scenarios. In other words, different strategies, right? One possible strategy is increase your monthly deposit, right? Another possible strategy is find a bank that pays higher interest rate. Okay. Still, another strategy is, what if you extend your timeline, right? You extend your timeline by 1 year. Okay. See, there are 3 possible different, scenarios, and right. In all these different scenarios, you can compare with, in a single shot. That's the beauty of Excel, because you don't have to do it one by one. Now, all you need to do is simply, because they are all, using the same formula, you simply highlight these 3 cells at the same time, right? Select these 3 cells simultaneously, right? And then you can drag it down simultaneously, and then all of the results are automatically calculated, and so you can compare them in a single shot. And then this is, as I said, this is the beauty of Excel. You don't have to do them one by one every time, right? Now, the second scenario, right? Second strategy, if you increase it by $50, you got a lot closer. But you're still about $700 short, right? So that means you are close, right? So it's only a matter of, increasing, fine-tuning, right? But again, fine-tuning will, require trial and error. In other words, you will have to try out different numbers. It's called trial and error method. And trial and error is still a very crude method, because it is, not very time and resource efficient, right? You have to put in your time to try out different other values, right? And we don't know how many trials it will take to nail the exact 60,000, right? Now, a third scenario, higher interest rate. Now, 8% it may not seem very impressively higher than 6%, but in a banking industry, right, in a financial industry, 0.25% difference is a huge difference, right? Banks, as I told you, banking is a very competitive industry, right? You really don't find another bank that pays, significantly higher interest. Significantly higher means something like, greater than 0.25, 0.5, right? So this is almost unrealistic. But just for our thought experiment, we can do that. And even if they are paying 2% higher, we are closer, but we are still about, $1,200 short, right? What if you extend your timeline by one more year? Well, then you more than overshoot, right? You more than um, reach your target future value, right? You even more than reach it. You overshoot it by 9,000. Well, this is, you might say, wow, I would like that. I mean, I would, of course, who doesn't like this? But then that means you're postponing graduate school by one year. Well, if it doesn't matter, that's fine. But if it matters, then that's another story, right? So our next question is then, is there a way we can nail the exact payment, right? Instead of going through trial and error, can we nail the exact payment? Yes, we can. We'll definitely talk about it later. But here, what about this column? The column H is the column of annuity due, right? That lowercase d at the end stands for annuity due, okay? So how do you find annuity due? Well, didn't I tell you when we were doing that, when I was showing you that scaled down version of example, the only difference between ordinary annuity and annuity due is just one more compounding. So what does that mean? You can recycle the ordinary annuity result, right? And simply give it one more compounding, right? Simply give it one more compounding. It makes sense? So if you do that, that's annuity due is, drag it down, okay? We get our future value by annuity due, okay? All righty, so well, that's the first part of this lecture, and then we will need to take a break and come back to the second part of the lecture. Okay, so end of video. Stop recording.